Welcome back to another explainer. Today, we are decoding the hidden rules of numbers. Think of the entire mathematical universe as this incredibly exclusive VIP club, and today, we're going to find out exactly who is on the guest list and who gets permanently turned away at the door. Okay, let's dive right into this. Is the number 0 a rational or an irrational number? Seems like a pretty simple question, right? Well, in the math universe, 0 has a very specific identity. To figure out exactly where it belongs, we first need to understand the strict entry rules for our VIP club. Section 1, the Rational VIP Club. Getting past the velvet rope into this club requires a very specific, undeniable ticket. A rational number is defined as any number that can be written as a fraction of two integers. We usually call this the A over B formula. Basically, if you can format your number with an integer A sitting neatly on top of an integer B, congratulations, you've got VIP access. So the absolutely crucial point here is that while both A and B must be integers, B can never, ever equal 0. If that bottom number is 0, the whole mathematical logic just completely falls apart because you literally cannot divide something into 0 parts. Think of that rule as the strict bouncer standing right at the club store. Let's look at the simple fraction 3 over 4. It fits our VIP criteria flawlessly, doesn't it? 3 is an integer, 4 is an integer, and most importantly, 4 is definitely not 0. It's clean, it's simple, and it undeniably gets the VIP treatment. Which brings us to section 2, rationals in disguise. Now, you and I both know the math universe loves a good plot twist. Not every number walks up to the club looking like a neat little A over B fraction. So, let's finally answer that opening question. Take a standard integer like 5. It doesn't really look like a fraction at first glance. But if you just put it over a 1, making it 5 over 1, boom. It hasn't changed its actual value, it just changed its outfit. And 0? Well, 0 can easily be written as 0 over 1. 0 is an integer, 1 is an integer, and the bottom isn't 0. Mystery solved. 0 is absolutely a rational number in disguise. And the disguises get even more clever when we start talking about decimals. 0.75 might look like a regular decimal, but it's actually just 3/4 in a trench coat. It's a terminating decimal, which means it stops. And then we have 0.333 repeating. Even though it goes on literally forever, it's completely predictable. It's really just the fraction 1/3 showing off a bit. So this gives us a definitive rule you can always rely on. A decimal is always rational if it terminates or if it repeats. If it has a clean stopping point or if it gets stuck in an endless but completely identical loop, we can always reverse engineer it back into a tidy A over B fraction. It is entirely rational. Let's move on and see how this builds, because all of this perfectly ordered math begs a massive question. What happens when a decimal doesn't stop and it absolutely refuses to repeat? What on earth do we do with numbers that just completely reject our golden rule? Section 3, the rational versus irrational showdown. We are now officially leaving the cozy, orderly VIP club and stepping out into the wild. On one side, we've got our rational traits, tidy fractions, and predictable decimals. But on the other side, we have pure mathematical chaos. Irrational numbers cannot be written as fractions, period. Their decimals are non-terminating and non-repeating. That means there is absolutely zero predictable pattern to be found. Let's actually name some of these famous rule breakers. Obviously, you recognize pi. Then there's the square root of 2, Euler's number E, or that wild sequence starting with 1.414. If you tried to write them out, their decimals would stretch across the universe without ever stopping and without ever forming a repeating sequence. They are inherently, beautifully infinite. And this brilliantly illustrates the definitive split in our math universe. On one side of the scale, you have the predictable, ordered weight of rational fractions and decimals. On the exact opposite side, you have the infinite, chaotic weight of irrationals like pi. They are fundamentally opposed concepts, just perfectly balancing the scales of mathematics between total order and pure infinity. Which leads us to this kind of mic drop, bottom line rule of thumb for categorizing every single number you'll ever encounter. All rational numbers can be written as fractions, but all fractions are not irrational. It is the absolute defining line in the sand. So we've cracked the code on what makes a number rational, and we've peered into the endless void of the irrationals. But honestly, it leaves me thinking. If irrational numbers like pi perfectly describe the circles and the curves we see everywhere in nature, yet those numbers never repeat and they never end, how much of our physical universe is actually built on pure, unrepeating mathematical chaos? It is absolutely fascinating to think about. Keep learning, stay curious, and I'll catch you in the next explain.